Hey guys, welcome back to day 29. We're going to talk about cell potential and concentration today. So if we remember cell potential, right, that's a volt, and that is going to be equal to the work over the charge, right, joules per coulomb. So, and that happens to be E cell. Now charge, we'll use Q again for charge, Q. And since it's negative, the charge is negative, electrons are negative, it's negative Q. So therefore, the work out of the cell is going to be equal to negative Q E cell. Well, the charge, then, if we have a new constant, and that would be the Faraday constant, Michael Faraday, 96,485 coulombs is 1 mole of electrons. So every 1 mole of electrons has a charge of 96,485 coulombs. I think we talked about that briefly in a previous video. So the max theoretical work the maximum theoretical work we can get out of a cell would be equal to the charge, which in this case would be N, number of moles of electrons, times the Faraday constant, right, to give me the charge, that's Q, times E cell. And do we have a quantity that discusses the maximum theoretical work? Do we have a function that does that? And my answer would be delta G standard, then equals negative N, number of moles of electrons, the Faraday constant, times the cell potential. So just to recap our units real quick, N would be moles of electrons. F, again, would be coulombs per mole of electron. E cell is volts, which is a joule per coulomb, and delta G is in joules. So our units work out. And this is, of course, at standard conditions, which of course is 25 degrees Celsius, 1 atmosphere, and 1 molar for solutions. We can rewrite this equation. I'll just write it in blue. Delta G equals negative NF E cell, and this would be not at standard conditions. So that means if I'm at 20 degrees Celsius, the blue equation applies. Okay. So let's go back to one of our first examples where we had zinc solid going to zinc 2 plus and copper 2 plus going to copper solid. We actually had we had a voltage 1.10 volts. That was E standard for the Daniell cell. What is delta G for this case? So my question is, what is delta G? So delta G would equal negative NFE. Well, delta G standard, N, number of moles of electron. Well, if you look, it's 2 electrons, right? 2 electrons to there, that's the difference, and it's 2 electrons there. Obviously, it's going from zinc to zinc. They're not going from, they're going from zinc to copper. So the overall change is going, well, actually not there. Zinc to zinc 2. That's where it's going. Zinc to copper 2. But it's a 2 electron transfer, that's my point. So it's negative 2 moles of electrons, 96,485 coulombs per mole of electron, and 1.1 volts. So delta G is negative 212,267 joules, or negative 212 kilojoules. So there's delta G, standard, under standard conditions. That's our maximum theoretical work we can get out. Now let's look at non-standard conditions. So this is not at either 25 degrees Celsius or 1 atmosphere or 1 molar. And we're going to focus in on the concentration. Right, most of the time you've noticed in Chem 1 and Chem 2, I call it chemistry land in the textbook, everything's magically at 25 degrees Celsius. So that's pretty much going to be how we operate. But the concentrations are going to change. So if we remember, we have standard conditions and non-standard conditions. So standard, delta G, standard, equals negative NF E standard. And delta G equals negative NF E. Well, we can rearrange with, we need another equation brought into the mix. And that would be where delta G, under non-standard conditions, equals delta G standard conditions plus RT natural log of Q. If you remember this formula, where you have the change of free energy equals the standard change of free energy minus basically the conditions, RT natural log Q. If we're going to do, we can do some derivations here, and nobody pays attention when I do them in class. So we're just going to wave the chemistry wand that I like to do, and we'll get E, the measured cell potential. Let's use a different color. Let's use the light blue. E equals E standard minus R, T for temperature, N, number of moles of electrons, F, the natural log of Q, the reaction quotient. And this is the Nernst equation. It is the relationship between E cell and concentration. So at this point in every class, before I even go into what these units are for everything, I tell my students to remind them that on the final exam, you're going to get a strong titration. You'll get a strong, weak titration. And you will have at least one Nernst equation. This will show up on your final exam. You can count on it, right? You can take it to the bank to know how to do this. Now, we're going to do a lot of examples here in a minute, but it will be there. So E, of course, is volts. E standard is volts, which again, these are joules per coulomb. N, All right, so what's R? R is 8.3145 joules per Kelvin mole. T is temperature in Kelvin. F, of course, 96,485 coulombs per mole of electrons. N is number of moles of electrons, and Q is the reaction quotient. Now, in the book, in most books, all problems, right, except when noted, which are very few in this case, occur at 25 degrees Celsius. So that means temperature is a constant, F's a constant, R's a constant, and they like to make natural log into log, which you can do mathematically. So in the book, you give E equals E standard minus 0.0592 volts over N log of Q. These two are the same equation. So let me highlight this equation and this equation are the same equation, but this is only at 25 degrees Celsius. So therefore, if I ask you a question and it's not at 25 degrees Celsius, you cannot use this equation, the Nernst equation with the log. You'll have to use the natural log one. All right, so let's do an example of this real quick. Suppose that the cell, that Daniel cell, zinc and copper 2, right, has been operating for some time, and the concentration of copper 2 has been reduced from 1 molar to 1 times 10 to the negative 4th molar, which is 99.99% used up. Zinc's practically 2 molar now, practically doubled. What's the cell potential? So it's very important to write the reaction out. And our reaction would be zinc solid plus copper 2 plus going to copper solid plus Zn 2 plus. The reason I need to do that is it gives me Q. Q would be equal to what? The concentration of zinc over the concentration of copper 2. Now you might see where it's concentration of ox over red or something like that. I would just recommend writing the problem out and looking what you're doing and making Q like you've done. Getting fancy, trying to do shortcuts, I wouldn't do that. I would just do this. Okay, now E. Do you remember E standard? 1.10 volts. So E equals E standard. Now we can use either one. A lot of times we'll use in class minus 0.0592 volts because we're assuming it's at 25 degrees Celsius over N log of Q. So we're looking for E, 1.10 volts minus 0.0592 volts over 2 moles of electrons times the log. Now, what was zinc's concentration? Zinc is going to be 2 molar, and copper is going to be 1 times 10 to negative 4 molar. All right. Now, technically, the mole of electron here is already gone. It's already included into the units, so we don't really have to worry about that mole. It cancels. So our reduction potential that we actually get is 0.97 volts. So that's the Nernst equation. Now, of course, there's one more thing we want to talk about. If I go back to our notes here. Since we have cell potential and Q reaction quotient, you probably noticed that cell potential is related to equilibrium. We can't get away from that, can we? Equilibrium is here. So we know at equilibrium, Q equals K, and the cell potential will be 0. The actual cell potential. Again, E standard doesn't change, but E does. So we're going to throw in E equals E standard minus R, T, N, F, L, N, Q, right? We can substitute in 0 equals E standard minus R, T, N, F, natural log K. All right. So if we redo this, I get E standard equals R, T, N, F, L, N, K, or E standard equals 0.0592 volts over N log K. I have that. I also have delta G now equals negative NFE, and I also have delta G equals negative RTLNK, natural log K. So I have all these formulas. We have, if I have a reaction quotient, I can get delta G. If I have equilibrium constant, I get delta G. If I have equilibrium constant, I can get E as long as there's electron transfer. So if I throw in acetic acid here, what's N for acetic acid? It's none, right? 0, so it doesn't work. Okay, but if I have E standard, I can get the equilibrium constant. If I have E standard, I can get the free energy change. So it's kind of nice to have those. So that is free energy and equilibrium. In the next video, I'm going to do lots of examples. So hopefully that works. Let me know if you guys have questions. Take care. We'll see you next time.